later when you need it. So the first thing I want to talk about is the, my tissue got messed up again, the circulator and power divider, right? So let's go back to the quantum computer we have been seeing so far. This is the quantum machine, right? Which output the pulses, right? We studied before. Now you know what pulses they are, right? For example, a reading pulse. Right? How do you send out a reading pulse? You send out the pulse of the frequency that you want, and then it will go into here to mix up with the local oscillator, which has another frequency, bring you to a higher frequency. And then you will send down the attenuator. What's the purpose of the attenuator?
Get rid of
very good. Get rid of the thermal noise, right? But isn't that your signal will also get attenuated? So what will you do? Just start with a large signal. Yeah, this is and then when you go to the 10 millikelvin temperature, then you go for this resonator and then go for this tuber. We'll discuss later. And then you will see this circulator or isolator pretty often, right? So what are they? Let's just learn a little bit. I think some of you, did you learn the circulator in your 140?
No.
Maybe no, right? It's more like EM. Maybe you need to go to microwave component, right? So let's learn a little bit. So you already learn what is a two-port network, right? We do the S21 in your project for the resonator. So here, let's take a look at this three-port network. It probably is a passive component, yeah. So let's study first a general three-port network. Right, so this is just an extra, it's good to learn a little bit. So a three-port network, what do you get? You have a scatter matrix, which has 3x3 component, S11, S12, S13, S21, S22, S23, S31, S32, S33, right? Because you have 3 ports, okay? So there are some special property of this, okay? You cannot be simultaneously lossless, right? So if you want it to be lossless, what does it mean? It means this matrix is unitary. Maybe let me just put in the parentheses. So microwave is very similar to quantum mechanics. They are just, you even can see that many of the gates can be implemented as just a regular microwave port, except that your microwave port need to go up exponentially with the number of qubits. Otherwise, it's the same as just a quantum computer, right? Unitary. What's unitary? Unitary means that, do you remember the definition of unitary?
You don't change the magnitude.
You don't change the magnitude when you do the rotation. There are a few definitions, including U dagger times U. U also identity, right? And also the column vector, they are orthonormal. You may all forgot. Uij, Uj, maybe I just use the bracket notation, that will be easier. So this is also like a review, okay? Although this is for the scattering matrix, but unitary is still the same, equals to delta Ij. If you're on the same row, then it is unit length. If different row, different column, then they are orthogonal to each other, right? You cannot be simultaneously lossless, reciprocal. Reciprocal means what? Symmetric. It's not a symmetric matrix. That means Sij equals to Sji. Okay, symmetric matrix, right? It means you draw a diagonal here, right? You flip it. S21 equal to S12, S31 equal to S13, S32 equal to S23, right? And, right, I say cannot, okay? And match at all plots. What do we mean by matching at all plots? It means we can put a matching network so that there's no reflection. So S11 equal to S22 equals to S33 equal to 0, right? So let's recall how do we do the plot. I hope that I have the convention correct, but I forgot. I might write it wrong if I don't do it correct. So we have V1 plus, right? V2 plus, V3 plus, correct? And then you might have this V1 minus, V3 minus, and then V2 minus, right? So your signal goes in, some of you go to other ports, some will get reflected, right? So when we say S11, S22, S33 equals 0, because if we try to match it correctly, just like a transmission line, then you have V1 minus divided by V1 plus equals to V2 minus divided by V2 plus equal to V3 minus divided by V3 plus equals to 0. I think this direction is correct. Yeah, is that okay? So it's good to understand. And so do you understand what is lossless? First, of course, it's really you don't consume any energy. You just pass the whole pulse to the next two ports. Symmetric, it means you go from this port to, is the same as going from another port, right? Or just like the matrix is symmetry, right? So it is reciprocal. And then you cannot match at all ports. This is like if match. If you match it, right? And the only way to match a RF circuit is to terminate it, right? For example, I have a transmission line. And then if I match it with the impedance, for example, with a resistor, right? Then there will be no reflection. Right? A transmission line is like you put a pulse to it, and then you keep going on. But eventually, if you see some change of the impedance, characteristic impedance, you will get reflected, right? Just like a wave. You may have a wave on a pond where you have a shallower place and then a deeper place. When you go from the deeper place to the shallower place, you will get reflection because the impedance is different. It's just purely wave theory. Okay, any questions? I know, yeah.
Is it cannot be reciprocal or only reciprocal?
Cannot be simultaneously lossless, reciprocal, and match at all ports. You cannot have all of them at the same time. Okay. Cannot have three wishes at the same time. Okay? There is a problem of any three-port network, and circulator is one type of the three-port network.
Can you do?
Okay, yes, we can have two of them at the same time. So let me prove to you. Should I prove it? Maybe I just write here. I just added more than what I want to say, right? Now, so this is what you just said, right? So this is three-port network. Cannot be simultaneously, three of them. But, for example, if we make it not symmetric, right? Probably now you will see why we don't want to make it symmetric, because then we can use it as an isolator. Then, okay, who have lossless plus match plots. Okay, so that is that answers your question, right? And this one is a circulator. Okay, so a circulator is not symmetric because it only go in a certain direction. Okay, I will show you how it go, right? It has 3 ports, you will just put this port 1 to port 2 and then port 2 to port 3 and then port 3 to port 1. Okay, your signal will go through in this way. But your signal will not go from port 3 to port 2, for example, in this clockwise direction. So I put a signal into port 1, all of them will go to port 2. And then all those go, if you have signal go to port 2, all of them will go to port 3. Okay, but you cannot have signal go to port 2, port 3, and then go off to port 2. So that's not reciprocal. Okay, so if you don't require the symmetry, then you can have lossless and match port at the same time. Okay, so in this case, so in a circulator, as we say, it is okay to not to be symmetry, right? But we just say that it is lossless and also match. We can make it match, right? We can attach some external loading so they match. When they match, it means S0, S11, S22, and S33 are 0. Look at this, right? Because there's no reflection, right? Whatever goes in won't come back. It will just go to other ports. Yeah. Yeah, because diagonal is the reflection coefficient, right? This is talking about how much you will get V1 minus divided by V1 plus, which is S11 by definition. Gamma for your 2-port system. Yeah, right, yeah. I think it's gamma, yeah. Okay, so that's the first thing. And then I cannot say that it is symmetric, so this one I need to still put S12, S13, and then here I am going to put S21, S23, S31, S32. Okay, so let's look at something, right? If it is lossless, an ideal case, it means it's unitary. Okay, so by definition, what is unitary again? Every column is a unit vector. So S21 square plus S31 square needs to be equal to 1. Do you see this? Unitary matrix means every column or every row is a unit vector. So this is a 3-dimensional vector, x, y, z. Like, of course, not the real space x, y, z, right? But the unit vector. Just like what we did in quantum computing, right? But now you can have 3 by 3, but in QB it either 2, 4, 8, 16, right? You never have 3 by 3. But it is unitary, means this column as a vector, right? This is just like V1, V1. I call this V1, V2, V3. And what I'm saying here is just V1 square equal to 1. That is what I'm talking about. Right? Of course, V1 square is V1 inner product with V1. Remember, this S1, S scattering matrix can be complex. So that's why we need to put the magnitude, complex coefficient.
What does that mean that it's lossless?
Just by definition, lossless needs to be unitary. Because you think about the whole power, because unitary does not change whatever you put in, right? Then your total power will be conserved, right? You still have the same length.
We say that each column is an orthonormal, or the set of the columns form an orthonormal basis.
Yeah, they form the orthonormal basis, yes, because they are orthonormal to each other. Yeah, you can say that. So using the same criteria, I also know that S12, this is 1, 2, plus S32 square equal to 1, S1 free square plus S2 free square equals to 1. Is that okay? And what else do I know? This is just normal, right? Normal vector, right? How about orthogonal? I do the first two rows. I call this 1, 2, 3, right? And this is 4. S21 complex conjugate. No, this one does not work. I don't need this. Maybe I write it one time. 0 times S12 plus S21 complex conjugate times 0 plus S31 complex conjugate S32, which is just V1 inner product with V2 equals to 0. I'm trying to do the inner product of these two columns. Right? Again, this is a vector because I have three components. I can call it a vector, right? I'm just talking about this three component. I call it V1 and V2. I do inner product. 0 star, I can even call this 0 star. The complex conjugate of 0 times S12 plus S21 complex conjugate times 0 plus S31 complex conjugate plus times S32. This is just the inner product of V1 and V2. They need to be 0 because it is unitary. I assume it is lossless. Do you see this? Any questions? So this one tell me that S31 star, S32, right, equals to 0. Now similarly, what else do I have? Can some of you, let's do V2 and V3. What's the final result? I'm talking about inner product of these two. What's the equation? S12 star, S13, plus 0 star, so it's 0, so I ignore it, and then again plus something times 0, right? So this is equal to 0. Right? I get one more equation. Then the last one is the first one, V1 inner product V3, which tells me that it is S21 star times S23 equal to 0. Correct? These two. Yeah? Okay. I know lots of math, but don't worry. Now the question is, look at this case 1. Look at this. Let's do it one by one. I start with this. This number times this number equal to 0. Then one possibility is S12 equal to 0, right? So I start with S12 equal to 0. If S12 equal to 0, where's S12? Here. If S12 equals to 0, then S32 must have a size of 1, right? So from equation 2, this is equation 5. Then I have S32 equal to 1. I just assume it is 1. Magnitude equal to 1. Is this okay? S12 is 0, right? I assume. Then S32 equal to 1, right? Now, so if S32 equal to 1, where's S32? Here. S32 equal to 1. Then S31 must be 0, right? Because 1 times something equals 0. Then S31 equal to 0. Now, if S31 equal to 0, then S21 must equal to 1, right? This equation. Correct? So from equation 1, I have S21 equal to 1. And repeat, S21. If S21 equal to 1, no. What I'm talking about, S21 equal to 1, right? Not 0. Very good. If S21 equal to 1, S23 must equal to 0, right? Something times something equals 0, so the other thing must be 0. And if S23 equal to 0, then S13 must be equal to 1, right? Equation 3. Is this okay? Any questions? So what does the matrix look like? S12 equals to 0. S13 equals to 1.
Can it be like a phase?
Yeah, so here I don't write the phase from here on because just a special case. So a good point, right? I did not write the phase. You can write the phase for a general case, but here just show this, yeah. So S1213 is equal to 1. What is S21? 1, right? And this is 0. What is S23? 0. And then what is S31? 0. S32? 1. It becomes a very simple matrix. How am I going to draw this? If this is port 1, this is port 2, this is port 3. You see that whatever goes into the port 3 will become the output of port 1. How do I see that? For example, right? The best is just to do a multiplication. 0, 0, 1, 1, 0, 0, 0, 1, 0. If I have something, let's say P3 goes in, this is the input to the port 3, right? What do I get? Maybe the best is, let me make it more general. Let me just call this A1, A2, A3. What do I get as the output? Remember, scattering measure is telling me that I have some input from 1, 2, 3, and then what are the output at 1, 2, 3? So now input 1, 2, 3 is A1, A2, A3. What is the output? Just do matrix multiplication. A3, the first one is A3, right? Because 0 times A1, 0 times A2, 1 times A3 becomes the first column, first row, right? And then how about the second one? A1, A2. So basically say A1 will go to A3. No, sorry, say the wrong thing. A3 will go to, port 3 will go to port 1, right? Whatever you put in port 3 will output from port 1. Because your input is at port 3, right? Port 3, right? And this is port 1, right? Maybe difficult to see. All the first column is port 1, port 2, port 3. And this is the input, and this is the output. Very confusing, but do you see it? Because this is input, I have A1 at port 1, A2 at port 2, A3 at port 3. After this scattering matrix, I have A3 at port 1. Right? And then I have A1 at port 2, A2 at port 2. It means what was originally at port 3 emits from the port 1. Right? What was originally at port 1 emits at port 2. And then what was originally at A2 emits at port 3. Is that clear? I hope you can ask now, right? At this class, I don't know how to teach. I don't teach well, but the best is that if you have anything, any doubt, just ask and learn it. I may not test this in the exam. And this is not in the homework. I already gave the homework already, assignment 4. Okay. Any question? Make sense? The phase? Yeah, so here we only prove that the magnitude of S13, S21, and S32 equals to 1. We did not talk about the phase, right? So here is just a special case. Yeah, he was just trying to say that I cannot put 1 because I only proved that the magnitude is 1. So maybe I should put e to the power I51 to be general. Yeah. Okay. Then what does it mean? Port 3 goes to port 1. Port 1 goes to port 2. And that is the symbol for this circulator is clockwise. You look at this circulator, you see that whatever in port 1 is going to go to port 2, where port 2 go to port 3 go to port 1. Okay? So I won't I don't have space for another thing, but you can also start from another term. Here I start from what? S12 equals 0. But I also can have S13 equals 0, right? It still satisfies everything, right? So if I start with S13 equal to 0, then I will go through the same thing. I get another scattering matrix. S equals to 0, 1, 0, 0, 0, 1, 1, 0, 0, okay? And if you just go through the detail, yes, it just rotates in the opposite direction. Okay? What you have is just when you have a port 2 input, it goes to port 1. You emit energy to port 1, it will emit from port 3. If your energy goes into port 3, it will emit from port 2. Okay? Yeah, it's just that here I say that I have a matrix that is lossless. It's not symmetric, right? And it is matched. All the ports are matched. Then I came up with these 6 equations. And this 6 equation has 2 possible solutions. One is that rotating in this direction. Another is rotating in this direction. Again, I have S12 times S13 equals 0. I can choose either S12 or S13 equals 0. First case, I make S12 equals 0. Then I get this clockwise circulator. This one, I choose S13 equals 0. I get the counterclockwise circulator. Okay? So this is the circulator we use in the circuits also. But then I want to talk about another thing called isolator. So what is isolator? It's very easy. It's just a match circulator. It's like this. Am I recording the video? Again, I have port 2, port 1, port 3, right? So originally, I have which matrix? I have the S equals to 0, 0, 1, 1, 0, 0, 0, 1, 0. From here, 0, 0, 0, 1, 1, 0, 0, 0, 1, 0, right? So this was the original matrix. But I'm going to terminate this one by a matching network. So that did I say something wrong? So let me see. Let me think a little bit. I get screwed up. I mean, what I'm trying to say is that I don't inject anything into here, right? So it is still matched. It is matched because we have been matching it already. So this is a little bit confusing. But what I'm trying to say is that here is no this is just no input. Okay, so all your input is just like this. The input will be just like this. This is still the scattering matrix, but your input is only A1, A2, and 0. Okay? Then what will happen? This is going to be equals to 0, A1, and then A2. Do you see that? What does it mean? It means port 1 is always 0. It means nothing comes out from port 1. Maybe I make it too complicated. Maybe an easier way to say this is that the signal you go into 1 will go out from port 2. The signal you go into port 2 will go out to port 3. The signal going into port 3 will go out from port 1. Now I don't have any input into port 3, so there will be never any signal go out from port 1. And here again, whatever goes into port 1 will go out to port 2. Whatever goes into port 2, what will happen? Where should it go? Should go to port 3. But because port 3 is matched, it's gone. Right? So from our perspective, this is an isolator. I only have signal going from port 1 to port 2. Any signal from port 2 cannot go back to port 1. Make sense? Only has signal going from port 1 to port 2. Okay, you only go in that direction. You cannot go back. And that's why it's an isolator. Now you look at this. We don't want any signal or from the room temperature or back going back to this qubit. So that's why an isolator will be put here. And there may be a servo isolator, depends on that. I'm not familiar with those. But you will see isolator made with this circulator. Now, so circulator is usually made of ferrites that you have this anisotropic material, which I don't know well neither, right? If you're interested, you can go into deep, read Porza's book, okay? Are you using Porza's book for your textbook? Okay. Okay, so that's what I want to introduce, right? Yeah, question?
Sorry, what makes it so we don't pick the other direction of propagation, in which case?
Because the circulator is just that you propagate in the clockwise direction, right? From 1 to 2, 2 to 3. And in this case, because we don't have signal going to 3, since we ground it with the matching network, then you always don't have signal going to 1. For this one? Yeah, then in that case, you just connect it in the right way. It will be the same. They don't exist at the same time. Yeah, so you depends on what circulator you have. For example, here I can just ground maybe port 2. Then you always go on port 1 to port 3.
So it's just like a property of the device.
Sorry, I did not discuss this. Port is just like a circuit. You have input and output where you access. This is the access point to this bulky circuit, right? For example, a very simple one yeah, it's just like the port in the project. But if you, from a circuit point of view, right, you can have an input. And then this is the output. For example, this is an amplifier. And then we can say this is port 1 and port 2. And then you may have many ports because this is a simple one. Yeah. Is that okay? Make sense?
Yeah. Inside that circle is just some microwave device.
Yeah, very complicated. It can be very complicated device. This is actually a simple device. Yeah.
And then whoever manufactured that device tell us what the scattering.
The scattering matrix is determined by what is inside this circle. Yeah, you're right. Yeah.
Matching network? What's that?
Say a matching network?
Yeah.
So it is like matching resistance. Or just in simple case, if you have an infinite wire, they have some characteristic impedance, you apply a wave to it, the wave will keep propagating forever if infinite is wrong. But usually it is not infinite. And when you stop it, when you hit the boundary, it's going to get reflection. It's just like the quantum mechanical wave, right? And if you terminate it with a proper impedance, which has the same characteristic impedance, look into there, then you don't get any reflection. So this is so-called matching. You match the impedance. Yeah, thank you. Yeah.
Can you just mention which part? Sorry.
Which part? It's just along this path, right? So this part actually depends on the structure. Some of them you have circulator already, because what I'm showing you doesn't need the circulator, but sometimes the qubit is like this. You go in, you have a microwave signal, and then you want it to go into the qubits, right? And then, or the resonator, and then you want this one to come back to the readout circuit. Then what do? You cannot just connect it, because this signal will lead out to readout circuit directly, right? So what we can do is put a circulator here, so that this signal will go into the qubit, and those reflectors from qubit will go out to the readout circuit, right? Just like the turnaround, what do you call it on the traffic? What do you call that one? Roundabout. Yeah, that's how you do that. That is for circulator. But if I ground it, then I can also have an isolator that I only force it to go this way. And this also just like roundabout, the same. Now the traffic can only go this way, but I brought another traffic on the third terminal. No cars can come in. Then no car can come to my lane, right? And I always go into that lane. And whatever comes from the other lane, they need to go to the one that I blocked it.
Does the heat from that just get dumped into the back?
The heat?
Yeah, because I mean, imagine it's going. It's just, or it's a small amount of heat.
You mean this one?
Yeah.
Oh, yeah, the energy will just dump into there, to this circuit, yeah.
But that's in
Here is more about the noise. You avoid the noise coming back. Yeah, tiny, yeah. But definitely it has an effect, as you said, yeah. Okay. Just an appreciation of what's going on, right? Now, how about look at this? This is called tuba, traveling wave